This video file was recorded in Sabunja University during recitations for the CS204 Advanced Programming course as it was given in the spring semester of 2017.
But previously, namely, you remember when we defined a new array by pointers. So this array guy is pointing to the first element basically. Now I can access the first, the second, of any element in this manner. If I want to print, let's say the first element, the one with index 0, I can do it like this: array 0. Okay. I can also do it in this manner: array plus 0. I'm writing it on purpose because it's not going to change anything. So when I say array plus 0, array is 300. Plus 0 is still 300, but I should put here a star. Okay, so if the value here is 5 of this integer, the output here will be 5, and also it will be 5 here. Okay. If I want to print the second index, very easy. I'll put 2 here, and let's say if the value of the index 2, meaning the third element, is 10, the output will be 10. Okay? Plus 2 here also. Okay? So array is 300. 300 plus 2 plus 1 is 304. Plus 2 is 308. Yes. So array will be 308 in this case. But because of this star here, we are printing the value of the content of the address of 308, okay? And it's 10, that's why I'm printing 10. Or if I want to generalize it, if I want to print the ith index, I do it like this. Okay? But remember, this star is here. And I forgot to put it. I mean, it was not our main concern, that's why somehow I skipped it, but you should have a star here in order to print the value to which the array is pointing. Because array is a pointer, and we print the value of array by putting this star here. Now let's start with a new topic that we saw during the lectures on Monday. Stacks. Do you know what stacks are? Yes, you know. Stacks are data structures when you are allowed only to put elements on top of it and to push elements, to extract elements from the top of it. Let me erase the board. Any questions about this stuff first? No? Okay. So, let's say that this is our stack, our array. Basically, it's an array. When I put an element here, I call it push. So let's say I'm calling the function push 5. And I have 5 here, okay? I'm calling push 7, and I have 7 here, okay? When I'm calling push, let's say 11, and I have 11 here. Always when I put an element on the array, I put it on top. That's why I have not a pointer, an integer, which points to the index of the last pushed element. So when initially that top was -1. Why? Because this is index 0, this is index 1, this is index 2. When I pushed 5, top became 0. When I pushed 7, top became 1, meaning that this is the most recently pushed element in our stack. When I pushed 11, which is index 2, top became 2. Now, yes? What's the? Integer. Let's assume it's integer. It can be any type, but in this case it's integer to make it easy. The type of the top is the index, and the index is always integer. Okay, but this guy here, 5, 7, 11, can be anything. Might be a string, it might be a pointer, whatever. Okay? But if you're using an array to keep those elements in our stack, and arrays have indexes, so top is index, an integer, always. Basically, I keep the index of the last pushed element. When I use pop, and I don't have to give any parameter here, I always take the element from the top of the stack. Okay, I cannot take it from the middle, from the bottom. I always take it from the top. So I push on top, one above the other, and when I take always from top, one after another. So this is a data structure that, so when I say pop, basically I take 11, and the top is decreased by 1, meaning that the next element I'm going to take from the stack is going to be the one with index 1. If I say pop again, then I'm going to take 7, so I don't have 7. I decrement top to be 0 now. And if I take 5, let me pop it also. Let's say I'm taking it. Top now will be -1, meaning that I don't have an element to take from. Okay, the stack is empty. When I define an array, it might be full. Okay, so we have to check about that. If the stack is full, we don't have place to put any more elements on top of it. We define a function which is called isFull, and we cannot put elements on top of it. So these are stacks. Stacks work in first in, last out. So you remember the 5 was the first to go in stack, but it was the last to be popped. Okay, so first in, last out. Or you might say last in, which is push, but it was the first to go out. Last in and first out. This is how stacks work. You remember we had dynamic and static stacks. With static stacks we had limitations of the array size. It was limited, but with dynamic stacks we had this linked list. Okay, basically this is how we use linked lists, simply linked lists, to implement a stack. This is top. Initially it's, now here it is an index, but top here is a pointer to the first node. Okay. Okay. When I added a node here, no. So this was the first, let's say the node, the list, the stack is empty initially, so top is no. When I add the first node, it looks like this. I have only one element on the stack. Let's say it's 5. When I add another one, it's like this. So top points here now. And it's number 7. Okay, push 7. When I add another one, let's say 11, then top points here. Okay. When I push them in reverse. So this is the first one that I'm going to take. When I say push, when I say pop, when I take them, I take 11, print it, process it, whatever, and I'm pointing here. When I'm popping 7, and I'm pointing to 5, top points to 5. Then I'm taking 5, and of course top points to null. Okay? So this is how I implement the stack using linked lists. Okay? The advantage here is that I don't have to care about the size of the array, because I can put as many nodes as I want. Okay? But with the arrays I have to give a fixed size of the array, and the size of the array might be, let's say, 1,000, or you might say, okay, well, we can say 1 million of elements, but I'm never going to use 1 million. Yeah, but you're going to waste your memory. When this is not good. But with this approach, you're not going to waste your memory. When you need a block, when you need a node, you just allocate it from the memory. When you don't need it, you delete it. Okay? That's why this approach with linked lists is better. And you don't have to check whether it's full or not, because it's never going to be full. When I say never, you can use the whole memory you have that is available for you. Okay. If this is clear, now let's go with the third example for today, with the stack. Just remove the previous codes. And add DynamicStringStack. Here we have the string utilities function, which I'm not going to explain again. And now let's go and see what the dynamic stack is doing, how it's working. Okay, so we are going to use a node which is called stack node. In our case, it's a structure. We have the value which is a string and a pointer to the next. So basically our node here will look like this. This is next. Was the name next? Yes. And we have the value here, which is string. Now the most important part is the class itself, DynamicStringStack. Let's see what do we have here. It should be obvious for you till now. So this is the dynamic string stack. As a private data, we have the top. Basically, it's a pointer to a stack node. It's a pointer to a node like this. Then we have another function which is called getTopPointer. And as a parameter, it takes DynamicStringStack. Basically, it's going to return the top. This is what this guy is doing. We might do it without it, but never mind. So it's returning a pointer to a stack node, and the top is a pointer to a stack node. It returns the top. So getTopPointer, get t g t p, is a private member. What do we have as public here? We have the constructor. So we have the dynamic string stack. What do you think? What the constructor is going to do? Give me some idea about that. We have the push function. We have the pop function. And we have the isEmpty function. We don't have. Why do we care about the isEmpty function? Because if the stack is empty and we're trying to pop to take an element from a stack, we cannot do it. But we don't have the isFull function, remember from lectures also, because it's never going to be full, because we can allocate memory as much as we want, since this is a dynamic stack. Now let's go and see the implementations of those functions. So, obviously, the constructor, when we initially start, the top points to null because we don't have any element. So top is null. Now let's see the getTopPointer returns my stack top. So my stack is a dynamic string stack. Basically, it returns the top. It's easy. We are going to use it. Let's see the push function. We want to add an element in our stack, and this is how we do it. So, we create a new node. The name of the variable of the pointer to the new node is new node, and we set the value of it to be this element here, basically the string. Let's say it's CS204. So new node, its value is CS204, this value here. And it's pointing to null. Okay? When we don't explicitly tell it, it's pointing to null. But I think we should put this part here to explicitly tell that the next value is pointing to null. We call the function isEmpty. We are going to see what it is doing. Basically, if the stack is empty, and how do you know? Can you give it a guess when the stack is empty? Top points to null. If that's the case, the stack is empty. It's very easy. Okay? So when the top is null, when we don't have any element, and we are calling the push function, very easy. Top points to the new node. So this top was null, and now it's pointing here. And now we deal with that value here. New node next is equal to null. So new node, this is the next, is equal to null. If we want to push again another element, but in this case it's not empty, since top is not pointing to null anymore, then we go here, we say new, firstly, again, no matter what, when we want to push an element, we are sure that it's not going to be full. Okay, that's why first we do this part here. So new node is going to point to a new node. Let's say that the value now is, a new node points here. Now the stack is not empty, since the top pointer is not null. We go here, we say new node next is equal to top. So new node next points to top. Okay? And I say top is equal to new node. And this top now is pointing to new node. Okay? I don't have the new node when the function is finished. This pointer basically, not the node to which it was pointing, and that's it. I add it in the beginning basically. This is like the function add to beginning. Let's see the pop function. I want to pop this stack here. If it's empty, stack is empty, cannot pop. Otherwise, when it's not empty, this is what I do. You see, I'm sending this variable element as a reference, meaning that this value is going to be there. So this is the value inside of this node. And I have the function, and I have this empty, the element, and it's referencing this guy. Okay, so I'm saying, if it's not empty, it's not empty. I'm saying the element is equal to top value. So top, the value is this one. And I'm saying then temp is equal to top next, but okay. So I have a pointer, temporary pointer, which is pointing to top next. So temp is pointing here. When I'm deleting top, when I say delete top, I delete the node to which top is pointing. So I delete this one, but pay attention. This value is going to remain because someone else is referencing to the value of the node that I just deleted. Okay? So I'm deleting the pointer, those areas, borders of the node, but not this is. Okay? It's kept in the element. Element is equal to top value, and I keep it. And everything else is deleted. It might look strange, but this is how it works. So I deleted the node, but not the value itself, because I'm still referencing it with this variable element. And I'm saying top is equal to temp in the end. So top is pointing to temp, okay? And I have this in main, or wherever I called it. Again, if I call the pop function again, if is it empty? No. Then this element is taken as a reference. So this is the value of the node. This is the element. And it's referencing this value here. I'm doing it by this row here. Then I'm saying temp is equal to top next. Okay, so this temp is equal to top next, which is null. So temp basically is referencing, is pointing to null. I'm deleting the top, and when I'm deleting the top, I'm deleting everything associated with it. The next pointer, the boundaries, except for this value here, because the element is referencing the value. It's not deleted. And I can use it in main. Okay? And I'm saying now top is equal to temp. So top points to null. And when I want to pop an element, I'm asking, is it empty? Yes, it's empty because top is null. And I'm printing it's empty, you cannot do anything. Okay. Now the isEmpty function is trivial. We saw it actually. You guessed it. If the top is equal to null, the status is true. Otherwise, it's false, and I'm returning the status. So this is the CPP file. Now let's go to the main file and see what do we have there. But before doing it, let me first run the code and see what are we actually doing here. So in this stack, I'm entering numbers in postfix notation. So I'm entering 3, 4, 5, plus, multiplication, 10. Then I should enter the sharp. No, this is the sharp sign. Okay, so this is what I added, and this is how it's seen from the compiler. When I added 3, 4, 5, plus multiplication 10. This is postfix. The infix value is 10. And this is why... no, okay. This is the postfix, this is the infix value. 3 multiplied by 4, 5, and I'm taking the empty stack. Is there any mistake here? Just a moment. Maybe I've switched the codes. I should know where I have stopped. Okay. So I'm giving the values 3, 4, 5, then plus multiplication. Oh, this was my mistake. 10 and division. I didn't give the division. Yes. Now I give the sharp sign, and this is it. Okay. So that was my mistake. Okay. So this is in postfix notation, and this is in infix. Okay. You remember it from lectures, I hope, but I'm going to go through it very, very briefly. Let's see what I'm doing here. Let's see what postfix and what infix notations are. In infix notation, actually we have been used to use the infix notation since our primary school. So if I say something like this, 3 multiplied by 4 plus 5 brackets, all this in brackets, divided by 10. What I'm going to do first? I'm going to do this part first, then this part first, then this part first. Okay? This is infix. In postfix notation, it's different. What I'm doing is the following. I put everything in stack. So if I want to say 3 plus 4, I say 3, 4 plus. This is postfix. Okay? And some calculators use this way of calculating values and numbers, doing operations. Why? Because they use stack. Okay? And how they use stack? Well, let me tell you how it's done. So if I enter 3, 4, 5, so addition should be done first. So this is 4 plus 5 is done here. After the addition, I'm doing the multiplication. So 3 is multiplied by 4 plus 5. That's why I have the multiplication. And all of this is one number, is going to be divided by 10. Okay? That's why I have 10, then division. Basically, I should have one number, another number, and an operator. So this is the left-hand side, this is the right-hand side, and the operator is in between. Okay? This is how postfix works. So this is infix this is postfix. In means the operator is in between. Post means that the operator comes after the operands. Okay, it might be multiplication, division, whatever. So let's see why some computers and calculators use the postfix notation. Because it's easier for them to keep things in stack and how it can be. So let's start with this stuff here. I'm entering numbers, so I'm entering first 3. And if it's not an operator, meaning plus, minus, multiplication, division, I'm putting it on top of stack. So this is 3. It's not a number. It's not an operator. I'm putting it on top. Then I have 4, and I'm putting it on top. Okay. Then I have 5, and I'm putting it on top. Afterwards, I have plus. Okay. So when I have plus, I pop the first one. I pop the stack again. And basically what I'm doing, I'm using, so I pop 1, and so this is my right-hand side. Right-hand side. I've put 5 here. I pop the stack again. So top was pointing here to 5. I took it. Now it was pointing here. When I'm taking the top of the stack, I put it here. So this is the left-hand side. And I say that I have plus here. Then I apply the operator plus to those two. 4 plus 5. Okay? So 4 comes here, 5 goes here. I add those guys, and here I have 4 plus 5. And I push it. Okay? Now I'm taking the multiplication stuff. Okay, it comes. It's not a number, it's an operator. That's why I push this guy, and this guy comes here. So instead of right-hand side, I have 4 plus 5. Okay? The top now points here. I'm popping this also, and I put it here to the left-hand side. It's 3. And the operator was multiplication. Okay? That's why I multiply those two. And instead of this guy, I have what? 3 multiplied by 4 plus 5. So 3 multiplied by 4 plus 5. I can put them also on brackets. I'm not finished, since you see I take the number 10. And 10 is not an operator. That's why I put it on top of the stack. So I put 10 here. Now when I take the division, but the division is an operator, that's why I pop the stack twice. I pop the 10, and the 10 comes here. So the right-hand side is going to be 10. And the left-hand side is this one. Okay? So the left-hand side is 3 multiplied by 4 plus 5 in brackets, in parentheses. And I have the division, of course. So I apply the operator to them, and this is what I get. I have 3 multiplied by 4 plus 5 in brackets divided by 10, all of them in brackets, parentheses, okay? But instead of those parentheses, I could have done the operation itself, okay? So I could have added 4 plus 5, it's 9, multiplied by 3, 27, divided by 10, blah, 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 okay? But this is just to show you how things work. Now let's see, any question? Yeah?
Have you tried before to as in parentheses?
I'm afraid I didn't understand your question. So, can we put 10?
10 in parentheses after 3 or 5, and plus multiplication and division.
I'm afraid not. Because this is how it works. 3, 4, and here we don't have any parentheses. Here we have this stuff. Okay? But if you want to divide 10 divided by blah, 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 then of course you can put it in the beginning. But you will have another expression. But those expressions, this one and this one, this is in infix, this is in postfix, these are the same. Now so you saw how it was working. Basically, when I have a number, I push it. When I have an operator, plus, minus, division, multiplication, I pop two elements. The first pop becomes the right-hand side operator, on the right of the operator. The second pop goes to the left-hand side, okay, and I execute the operation. Here I'm not executing them, but I'm putting them on parentheses to show how things works, okay? Because I would have showed like the result is 2.7, but how did I get it? That's why I'm just appending these stuffs like string. So this is our output. Let's go through main and see how did we get it. So this is the main. Very easy. This is for postfix. This is a string. Postfix is this one, okay? So I keep track everything that I add. If you want, I can show it here to you. Because the infix is kept in the stack, but the postfix is not. That's why. Let's say that I'm defining a new string. So this is for the code. The string is postfix. Okay. Initially, the string is empty. So I'm reading data one by one up until I don't enter the sharp character. Okay. And let's say I'm adding 3 initially. So postfix is equal to previous plus postfix plus the string that I've entered. The string is now 3. Okay? So I'm entering 3. Postfix becomes 3. And I'm checking if the string, which is 3, is not equal to plus, minus, blah, 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 and it's a number, it's not an operator, I push it. That's why. This is our stack. In the stack, I push 3, as I showed it to you. Now I'll go again here. I'm entering the string. I'm prompting the user to give it. I'm entering now. I'm giving us an input 4, so the string is 4. And I'm adding this 4 to the postfix. So here I have 3, 4. Okay. And again, it's not one of those. That's why, since it's not one of them, I'm pushing it. So I have 4 here. Okay, again I'm entering another data, which is 5. Here I'm adding it to the postfix variable. So I have here 3, 4, 5. And I'm pushing it. It's not one of them. That's why I'm pushing it. Now when I have to enter the plus, the string is plus. The data that the user gives. Okay, and I'm reading the data, by the way, here. See, in the end, I'm reading the string, and I'm checking here whether it's equal or not to the sharp character. So I'm entering plus, and I'm saying string is not equal to plus. This is not true. That's why I'm going here. And here I'm taking, you see, I'm popping argument 1 and argument 2. Okay, 1, 2. So basically, I have argument 1. When I pop it first, I have 5. It's here. Then I'm popping the stack again. It's argument 2. This is argument 2. And I have 4 here. And then I apply the expression, which is equal to, I open the parentheses, argument 2, plus the string, and the string is plus argument 1, plus the parentheses. Okay, so argument 2, which is 4. So the expression will be, I'm going to write it again, because in the end, you see, this expression is going to be pushed in the stack. Okay, so I have popped those 2, and I am pushing, open the parentheses, argument 2, and argument 2 is 4. This plus is for concatenating strings. Then I'm appending, merging it with the string that I've entered, and the string is plus, so I have plus. Then I have argument 1, which is this one, so I add it here, plus I close the parentheses, and I close them. Okay? Then I go and I enter multiplication, so the string will be multiplication. Since the if clause will not be true, I'm going here to else. And again, I'm popping them. So argument 1 will be this one. 4 plus 5. And argument 2 will be 3. And of course, I'm adding it, pushing it. I'm going to try this one, and this is it. The result will be open parenthesis plus argument 2. So I'm opening the parenthesis. Argument 2 is 3 multiplied by argument 1, which is 4 plus 5. And I'm closing the parenthesis. Okay? And I go to the end. So in the end, eventually, I'll have, although I've entered this one, I'll have this infix notation. Okay? As I showed it to you. Let me run it again. So I have what? 3, 4, 5, multiplication, addition, multiplication, then 10, then division, and then I'm entering sharp, and this is it. So I've entered 3, 4 plus multiplication, 10 division, and this is what I get. Because in the end, so here is where I print the postfix, and the postfix is this one. Every character that I enter, I keep it here. I append it in the beginning. You remember? This guy here, no matter what, whether it's true, if it's true or false, I'm entering the newly added character in the end. Okay? That's why postfix will have this one, an infix. In the last element that is remained in the stack will have the infix notation. I know it might be tricky to you, but okay. And this is because I'm adding stacks, I'm adding elements 0, 1, 9, and something like that. But so I start from 0 to 10, and I'm converting integers to strings, and I'm pushing them to the stack, and then I'm printing the stack, and this is it. I mean, this is the easy part. Did you understood this approximately? Any question?
Is this more optimized? That's why you're using it?
For calculators, this is much better.
It's more like efficient?
Yeah, more efficient, because you might have a very long expression. It should look for parentheses, blah blah. It's hard. As you give elements, it's doing it on the fly. I mean, you understand what I'm trying to say, okay? You don't have to see the whole expression and start from the middle. You always start from the right. Okay? If you have plus, if you have number, just push it. If you have operator, pop two of them, execute the operator, and this is it. You don't have to check for parentheses. You don't have parentheses with postfix. This is how many of calculators work. So if you're going to design a calculator, probably you're going to use the postfix notation. But we're not used with that. Okay, any question? Yes or no? How many of you understood this example? The calculation. If you understood the calculation and you know what does push and pop mean, you will understand that you're home. So all of you, I suppose. You can check the video. You can mail me. I know it's a bit tricky, but this is a good example to show you where we can implement stacks and why we need them. It's not to complicate your life, but we learn about stacks because we are using them in our everyday life. Okay, now let's go with the queues. Can you tell me what a queue is? I don't think that I'll need more than 10 or 15 minutes about this one. But this is queues. When you go to a store or to a bank, the first customer that enters the bank and asks for a service is going to be served first, okay? So if we have customer 1 and customer 2 coming and comes customer 3 after each other, the first one that will be served will be the customer 1, then customer 2, then customer 3. I mean, basically they are served as they arrive. Okay? If it was a stack, then the last that came inside the bank was going to be served the first, okay? Which is not fair in this case. In some cases we should do that, exactly, but in some cases not. Or if you want to print something and multiple people are printing in the same printer, you send your printouts, your documents you want to print, and there's a queue there that takes your requests and prints them as they come, okay? So this is why we need queues. How does a queue work? It works in, first out notation. I'm going to show it how it works with linked lists. So that's why for the queues we have front and rear. Front means the first guy that came, and rear is the last guy that came, okay? So initially, like front, the head and tail, okay? So this is the front, this is the rear. It points here. When a new guy comes, okay, let's say there's only one guy waiting for service. When a new node comes, it's always added in the end, so the rear points to that guy, okay? Another guy comes and looks for asks for service. It's added in the end, and we represent end by this rear, okay? However, so we add them in the end. However, when we want to serve those nodes, we want to process them, we always start from the front, okay? So this guy is going to be served first, okay? That's why front is now pointing here. Then we have another empty slot to be served. That's why this is going to be served. So front points here, okay? Another one comes, it goes to the end, and rear points to that guy. So these are queues. First in, first out. Last in, last out. Let's see an example with queues. I think that you saw them on Tuesday, if I'm not mistaken, the dynamic example. But we're going to do it very briefly here as well. So, queue zipper. We are continuing with the queue zipper. As always, we will start with the header first, and then with the class itself. So let's see, what do we have here. In our example, the queue is going to be implemented by linked lists. We can do it with arrays, of course, but it's better with linked lists because we don't have to check whether it's full or not or whatever. This is the node of our queue. It's called queue node, and it looks like this. So this is the queue node. Basically, what we have seen. We have a pointer to the next queue node. And here we have the value, which is integer, of integer type. We have the constructor here. Value becomes num. The pointer points to the next point. If I don't send anything, if the pointer that I'm sending has no value, by default it's going to be null. Otherwise, if I don't send any parameter, this pointer is going to be null. Otherwise, if I send it, it's going to be that pointer. Okay? So this is the meaning of this pointer is equal to null. Now this is what we care about, the class itself. Again, we have the private data. In the private data, obviously we have the front and the rear, the head and the tail. So this is the front. It's a pointer to a queue node. And we have the rear here. It's also a queue node. What we have else? We have the functions inqueue, dequeue. Inqueue is putting new element, but when we put it, we always put it in the front. Dequeue, no, we put it in the rear. Dequeue is taking an element, and always when we dequeue from front. So, public enqueue dequeue. And is empty because when we try to take an element from an empty queue, it makes no sense. What do we have else? Clear. This is it. Now let's go with the CPP, the corresponding CPP file. When we first declare a new variable, obviously the front and the rear are going to be null. Okay, so this is null. The front is null. The rear is also null. This is just for debugging. An empty queue has been created. Okay. If we switch the mode to release, this is not going to be seen. It's not going to be printed. Let's go with enqueue. It's empty. What do you think? When the queue is empty? What do you think? So the stack was empty when the top was null. Here, where do we take from? The front should be null. If you don't trust me, just let me show it briefly to you. It's empty when the front is null, return true, otherwise return false. Okay? Meaning, if we don't have anything here to take, it's an empty queue. If it's empty, very easy, we create a new node, we make the front to point to that, and the rear also points to that. Okay? Because this is the first element. Basically, this is it. This is the new node. Both the front and the rear are pointing here because it's the new node. However, if it's not empty, then we say that rear next is equal to new queue. So rear is this one. We should add it in the end. Rear next is equal to new node. Okay. And we say that rear is equal to rear next. So rear is pointing here, but rear now is going to point to the newly created node. This is adding in the end. Okay. When we dequeue from the beginning. So this is enqueue and this is dequeue. If it's empty, of course, we can not allow it. Usually we exit the program, which is maybe not a good thing, but okay, we are exiting. Maybe we should just print that, okay, I'm sorry, we cannot exit. You cannot enqueue, but not exit. However, if we can dequeue, then you see the num, which is a reference there. So this is the value. And we have num. Let's say that the value is 3 here. Num is referencing this value. Then I'm saying temp is equal to front. So this is the front. Temp points to the front. Front is equal to front next because we're going to dequeue it. So front is going to point here. And then I'm deleting this node. But when I deleted this node, because the num is reference, it's not going to be deleted. Okay? And we will have it in main. So this is all about enqueuing and dequeuing. Now let's see the implementation. Let's see some stuff of usage of the queue. I'm going to run the code. It's very easy example. It will be over like in 5 minutes. So this is what we do. We are going to create 3 queues. One is going to be called odd queue. And in the odd queue, so this is the odd queue. We put some odd numbers, 1, 3, 5, 7, 9. Another one is going to be an even queue. So here we put those even numbers. And another one is going to be called the zipper queue. We take elements from both of them, okay? First starting from the odd, then from the even. So this is how we do it. So we take 1 from the odd queue, then we take 2 from the even queue, then we take 3 from the odd, then 4 from the even queue. But as you can see, we go till 9. And then we have yet 10 for the even queue, but we don't have 11 for the odd queue. That's why we continue with 10, 12, 14, 16 till the end. And in the end, we print the queue. Okay? This is what we do. How are we going to do this stuff? Let me show it to you here. Okay, so this is, let's say, the zipper queue. Initially, everything is null. I have the odd one. I'm going just to show you the front and the tail. So when I create this queue, this is the odd queue. So when I create this queue, this is what I have. This is 1, 3, till 9. When I'm doing the even queue, I'm creating it and enqueuing here. Those 1, 3, 5, and so on. Then I have the even one. This is front. This is tail. Not tail, rear, I'm sorry. Front, this is rear. And I'm enqueuing elements one by one. So I start with 2, 4, till I think it was 18, if I'm not mistaken. So rear points here. Then I take, while those are not empty, I take one from this, I dequeue it and put it here. So I put 1, and I don't have this one anymore. So front is pointing here. And I also take one from the even one and put it here. So I have 2. I take all of them. So I'll have 9 here and 10 here. And this guy will be empty. But this guy will not be empty, so I'll take all the rest of them and go until 18. Okay, so the rear is going to point here, and I'm going to print it in the end. How it's done? Very easy. So odd queue, even queue, queue zipper. Here I enqueue the values. I start from 1. You see I increment them by 2. So I put 1, then 3, then 5. To my odd queue. I start from 2, increment them by 2 in each iteration, and the even queue, I enqueue them 2, 4, 6, and so on, okay? Finally, I do this stuff. While my odd queue and my even queue are not empty, take first from the odd queue, dequeue it, and enqueue it to my zipper. Then take from the even queue, dequeue, and dequeue this element to my queue zipper. But eventually this odd queue, since it has only 5 elements from 1 to 9, this is going to be finished out. That's why we go out from the loop and we check. We are not sure why we are out of the while loop. It might be because of the odd queue, it might be because of the even queue. That's why we are checking. If my odd queue is empty, then take all the elements till the end and put it in our zipper queue. But it's not the case. If my even queue is empty, is not empty, then do this also. Fill the queue basically is dequeuing an element from this queue and putting it here. Okay? And finally I'm printing the queue zipper, which is this final queue here. Okay? Well, until it's not empty, dequeue the value and print it. This is it. Is this clear? Question? No questions. Okay. Good luck with your homework. If you have problems, mail me, or we can do some extra recitations here. See you.